Hi everybody. In this video we are going to go over 7.1, sampling distributions of means and proportions. And it sounds pretty technical, and it is pretty technical, but we're just looking at it at face value, and we just want to see, we're going to learn about a theorem called the central limit theorem, and it gives us a lot of power in statistics, and it's going to be basically used throughout the rest of the course. We don't have to understand the deep mathematics behind it. We just need to know what it says and what it means we can do. So let's kind of work into it and talk about why we have it and what we're going to do with it. And I also want to mention that, this section right here to me is kind of a turning point. And once we learn this is the last tool we need to begin tackling confidence intervals and hypothesis testing. For the rest of the course, from here on out, after this section, everything's going to feel pretty similar and procedural. We just got to kind of get through this because this is the last tool we need, and then we'll get to do, the whole reason we're studying statistics is to get to these tests we're going to learn how to do. So we're nearly there. So let's just talk about this section. Let's go through the lecture notes. It says, why statistics? Well, we use data from samples to make inferences about a population. And so here we're talking about a conclusion that's based on some sort of evidence or data. So for example, maybe we're trying to establish what is the mean height of all adults in the U.S. We've talked about this a lot, that you can't go ask or, you can't survey every adult in the U.S. and get their height. It's just not practical. So we've talked about the importance of sampling, but we never really, got too much into the details of what's the criteria for a good sample and what can we do with it. And that's kind of what we're going to learn now. So the idea here is that we're always trying to estimate some sort of population parameter. Remember, population parameters are things about the population we're trying to learn. So that might be, the population mean, or the population standard deviation, or the population proportion. Proportion, we haven't used that word a lot, actually, shame on me, but we've been using it nonstop. Remember, proportion is really the same as a percentage. It's just the fraction format of the percentage. So we've been doing tons of proportions, just been writing them mostly as percents or calling them ratios and not so much proportions. So just for example, let's say if 25 out of 100 people do something, you might say, well, that's 25%. Okay, that's the percentage. The proportion would be 25 out of 100, which reduces down to a fourth. So we've been working with proportions a lot. Typically, mean is, when we're studying some sort of quantitative variable, something I can add up, and then usually proportions, we're talking about a categorical type variable, like, in a certain population, what's the proportion that register as Democrat, or what's the proportion that are, Asian or some ethnicity. So anyways, let's talk about what we do with these. We're trying to estimate one of these parameters by taking a sample. And there's two things we really need out of our estimator, which would be like maybe our sample mean or sample proportion. We need them to be accurate and precise. By accurate, what we mean is on target. They're aiming in the right place. Precise, what we mean is that the results are tightly clustered around the target. They are hitting in the same spot or nearly the same spot consistently. With those two things, we can feel pretty comfortable that our estimator is doing a good job of actually finding the true value of one of these parameters. So, let's say the target is the population mean. That's what I'm trying to hit. The idea with these targets is, let's say we were talking about something that's accurate, but not precise. Accurate meaning it's on target, you're aiming right, but precise meaning that you're not getting consistent results. So maybe when you sample and you look at a bunch of sample means, maybe you're clearly aiming at the target because you've got the thing surrounded, right? So you're aiming right in the correct spot, but you're not that consistent, okay? Whereas something that might be kind of precise and not accurate is something where, let's say I'm trying to learn about the population standard deviation, so I'll look at a bunch of sample standard deviations, and so maybe maybe I'm being very consistent. Every time I take a sample, this is the standard deviation I get, and so I'm totally precise and consistent with my results, but my aim is off. I'm not pointed at the target, I'm pointed somewhere else. So that's just kind of like a visual of what the heck they're talking about there. We hope that that if we're trying to estimate a parameter like the mean, we hope that our sample means are on target and very tightly clustered. If those two things happen, we feel good about our estimate for the population mean. So this would be something that's accurate and precise. So that's what we strive for, and the tools we're going to learn are what's going to help us to do that. Okay, let's talk about some terms that we've used before, but maybe not quite in this way. We've talked about things being biased. So when an estimator is not accurate, that's when we would say that it is a biased estimator. So again, maybe I'm trying to estimate the population mean, and my estimator would then be my sample mean. And maybe when I take lots of different samples, I get a mean that maybe it's precise, maybe it's not, but it's clear that it's aiming for something else. It's aiming for something around here, when really the target is right here. So the aim is off. Something is pulling these sample means away from the target. That's one way we could think of something being biased. Okay, the aim is off. An unbiased estimator is accurate. It's on target. So if I'm aiming for the population mean, whether or not, again, it's precise, I'm at least clearly aiming right at it. I've got it surrounded, and we're going to work on getting the thing to be precise. A sampling distribution. This is something that we are going to be using a lot. And we've talked about distributions in the past, right? Some distributions we've talked about, we've talked about frequency distributions. Remember, that's when you list every possible outcome that can occur and then how many times an individual or a particular outcome occurs. We've talked about probability distributions. So that's when you list every outcome that can occur along with the probability of each outcome occurring. Now, this name is almost a little deceiving. Sampling distribution makes you think you're looking at a distribution of a sample. And that's not really what's going on. It's the distribution of a statistic. So remember, my statistics are the things we use to estimate a parameter. Statistics are like sample means, sample standard deviations. The sample proportion is P with a funny little hat. Right? P for proportion and P hat for the sample proportion. So we really are talking about a distribution of how these guys fall down. If we were to look at a bunch of different samples, what do the collection of sample means look like? Or what do the collection of sample proportions look like? Okay, so the sampling distribution of x bar would show all possible values that x bar can take on, and as well as how often we see it. Now, this is going to be incredibly useful for us, and it's we're going to learn a big theorem about this coming up in just a second. And so I just kind of want to show you what the theorem says. Hold on, I'm flashing ahead in the notes to see where. Let me pause it. Okay, I'm sorry, I got lost on where the theorem was about to be introduced. They introduce it on the next page, but I want to sort of just talk about the idea here of what the heck we're going to be able to do with this theorem. So again, we're talking about a distribution of, or sampling distribution, so it's a distribution of some statistic. imagine we have some sort of a population that's maybe really right skewed or something. Maybe more right skewed than what I'm drawing. If I want to calculate probability and really analyze data like this, remember you have to know a little bit about the distribution. If you're trying to find probability, you're trying to find area under the curve. This is a funky shaped curve, and we're not going to explore a rule that we could use to really calculate area under that thing. But here's a neat thing that we're going to learn. This is thanks to the central limit theorem. And I'm going to hop on StatCrunch and show you this. If I'm trying to learn something about this population, and I take a bunch of samples, so let's just say I take you, and then maybe I'm trying to investigate the mean. So I'll find their sample mean, right, the mean of those three data values, and I'll plot it down here. And then maybe I'll do it again, and I'll take another sample of three things, you, and you, and I get a sample mean out here this time, and I go ahead and plot it. If you were to do this a lot, I mean a lot, what you end up getting is a distribution that's normal, right? That's bell-shaped. Now, bell-shaped curves, we know how to analyze those and find probability, and that's great. It's very easy for us to analyze and study a normal distribution. And what this distribution would be, this would be the distribution of sample means. Well, that would be very useful for us. I mean, say, for example, I want to know, okay, if I were to go out and select a group of 50 U.S. adult males, I want to know what their average height is going to be, okay? We're going to get into many applications of why you would want to use this and why you would need to know this. This little idea here, that's what the big theorem we're going to learn about. Central limit theorem tells us that this is true. This is brought to you by Central Limit Theorem, which is going to get a little more formally introduced in just a bit. Okay, so let's just finish off these notes, and then let me hop on StatCrunch and show you a better visual of this happening. So here a little more information about sampling distribution. By looking at the sample distribution of a statistic, like we did here, we can see how good of an estimator the statistic is in estimating a parameter. That and the big fact that it's really easy to work with normal curves, right? A lot easier to learn something from this curve than from this right skewed curve up above, the original population. Okay, so here's a lot of notation. Make sure you know this stuff, okay? Parameters. Remember, the parameters are the things we want to learn about the population, right? So that would be the population mean, the population standard deviation or variance, the proportion of a population, right? This could be, again, the proportion of all registered voters in America, the proportion that are registered Democrat, okay? Our statistics have to do with our samples, and those are our estimators. Those are the things we're going to use to estimate the parameters. And those would be sample mean, sample standard deviation, sample variance, and proportion of a sample. Again, p hat. Some other funky notation here, or new notation, and it gets easy to trip over the words here, is the mean of all sample means. Okay, so it's mu, right? It's the mean, sort of a population mean of all the sample means. Okay, and we have the standard deviation of all the sample means, and n we're used to as being a sample size. Okay, let me hop onto StatCrunch and let's take a look at a visual of this of the theorem that we're going to talk about in action. Okay, I want to hop on StatCrunch, and they've got a cool little way to visualize this. So I'm looking under applets. These are all, the applets, by the way, are little pre-programmed sort of things you can do. Like they've got little games, you could run little experiments. They've got like a random number generator, and they've got a spinner for doing probability things. Anyways, they've got this thing on sampling distributions, and let's not worry about what all this is. Let me just pick something right skewed, find the mean. Let's look at this. Okay, let's talk about what this is. Does that help? Yeah. So this right up here represents my population. Whatever the heck it is, it's something right skewed, very right skewed. And they're going to visually show you what I just tried to show you on the notes. So let's take a sample size here of, let's say, 3. Wait a minute. Okay, so my sample sizes will be 3. So what they're going to do is they're going to take, well, let me just hit run. Let me just do this one time and show you what happens. From the pop, they take a sample of 3 things and find the mean. Let's do that more. Sample size 3, there's the average of those. Sample size 3, there's the average. Sample size of 3, there's the average. Sample size of 3, there's the average. 3 and the average. Sorry, I almost couldn't keep up there. So do you see what they're doing? From the population, they're taking a sample of size 3. Okay, and they are then finding the average of those 3 things and plotting that average down below here. Okay, so let's do 5 more times. There's their average. 3 data points, that's their average. 3 data points, that's their average. 3 data points, that's their average, and so on. Okay, well, what happens if we did this a lot? Let's hit 1,000 times. And don't worry, we're not going to sit through it. It just does it automatically. Look at the shape. Let's do 1,000 more. Let's do 1,000 more. 1,000 more. It's starting to get sort of uniform and bell shape. And actually, we can make this a lot better, and I'll show you in just a second. But something interesting happens. Here's the mean of the population. Here is the mean of all my sample means here. So it's like if I take the average of all the averages, I get really close to the actual true average for the population. Now my standard deviation is off. There's the population standard deviation. There's the standard deviation from all my sample means. So they're off, and that's supposed to be that way. There's actually a formula that links them together, but the means are the same. And the more times you do this, the closer they get. Now we had to do like 4,000 or 5,000 times to get something that looks not even really great bell-shaped. What we're going to learn is that sample size plays a big role in this thing. So let's reset this, I think, and let's try a bigger sample size. Let's do like 30. And let's see, 30. I'm not going to hit one time because then it's going to show 30 samples and it's going to do one average. Okay, so everyone trust me, it's going to draw 30 different things from all over slowly, and then it's going to find their average and we'll get one sample mean down here. And then, I would need to do that over and over and over and over and over again. Let's just say we did it 1,000 times. That looks way more bell-shaped than when I had a sample of just 3. So let me do it again. Another 1,000, another 1,000, another 1,000. Way more bell-shaped than when my sample size was just 3. And I wasn't looking at the means, but the mean will actually do a better job faster. The standard deviation is way different. Oops. Okay. Which again is supposed to be the case. We've got a formula to explain that. So sample size plays a big role in this. Now let's try a different one. Let's try something that was not right skewed, but how about uniform? So let's take something that's a box. Remember, uniform shows up as a rectangle. Let's see if we can turn this thing normal. So it starts with sample size 2. Let's just leave that and run it 5 times. 2 data values, their mean. 2 data values, there's their mean. There's their mean. There's their mean. And there's their mean. So there's 5 sample means here. We could do it another 5, and another 5, and see this thing start to build. Let's just jump to 1,000 times. It's, looking somewhat normal in the sense it looks more like a bell-shaped curve than a box. What if we do 1,000 more and 1,000 more and 1,000 more? You could see it's unimodal and symmetric, but it doesn't have much of a bell-shaped curve to it. Again, that's due to the sample size. Let's change the sample size to something bigger, like how about we do a sample size of, let's say, 85. Okay, again, I'm not going to hit 1 time or 5 because it's going to then do it. It's going to take 85 different data values, find their mean, and plot that one sample mean. Let's just see what happens if we jump to 1,000 times. We get a really nice symmetric bell-shaped curve. Another 1,000, another 1,000, another 1,000. Okay, and again, the mean of the population is really close to the mean of all these sample means. Rather, this guy is really close to the population mean. Again, the standard deviations are pretty wildly off. That's okay. There's a formula, again, that explains that. Okay, so hopefully this simulation helped get a visual of this thing going on. This is brought to us, again, by the central limit theorem, which we're going to define in the notes in just a second. So let me pause this and hop back to the notes. Okay, so let's talk about a sampling distribution of means. Okay, so first of all, when we looked at hold on, let me just get a little picture up here again. We had something very right skewed. That was our population. When we looked at a sample and took the mean, and a sample and took the mean, and a sample and took the mean, we said, oh wait, that becomes sort of uniform and bell shape, okay, normally distributed. And if we look at the mean of all of the sample means, that should be the mean of the population. It's definitely not how I drew it, but it should be the mean of the population. Remember, we saw the box for the mean and the box down here for the sample, and they were the same, right? Okay, or pretty darn close to the same. In fact, and the more times I did this experiment, the closer they got. But do you also remember that their standard deviations, the population standard deviation and the sample standard deviation, those were very off, right? Those were very off. You know what? I'm not using correct notation here. This isn't a sample mean, it's the mean of the sample means. And this isn't the sample standard deviation, it's the standard deviation of all of those sample means. I should be a little better with my notation there. We saw that these guys were pretty off. Well, there's the formula that brings that to us. So we knew that the means were the same, and we saw that the standard deviations were off. Well, it's according to this formula. The standard deviation of these sample means is equal to the population standard deviation divided by the square root of n, your sample size. Let me hop on the StatCrunch real quick and let's see. Okay, here's standard deviation of my population is 14.43, and the standard deviation of my sample means is 1.59. 14.43, 1.59. 14.43, that was my population standard deviation, and for the sample means it was 1.59. Let's verify that this formula is not lying to us. It should be that 1.59, the standard deviation of my sample means, is equal to the population standard deviation divided by the square root of my sample size. I don't remember what that was. This was a sample size of 85. So let's plug it in. I'm going to put this part in my calculator right now, and they should be pretty close. 14.43 divided by the square root of 85. This in my calculator is 1.57 if I round it. So yeah, pretty darn close. I was just rounding and things like that. So, and again, the larger n is, or the more times you do the experiment, the better this formula works, or the closer they get to one another. Okay. Well, this is really important because it's really important that I know these two features because, we've learned that if you have something that is normal, that it's easy to calculate probability because I've got StatCrunch or I've got z-tables. But basically, if I want to know the probability, which is the area under the curve, being left or right or of some value, I have methods to do it. But you have to be able to tell me a little bit about this distribution because remember, if you've got a very low standard deviation, very little spread, then your bell-shaped curve looks like this. This is low standard deviation. Because basically around your mean, all your data is really tightly packed around the mean. Okay? You don't have to go very far left or right to get a lot of your data next to the mean. Whereas if you're looking at something with a higher standard deviation, the bell-shaped curve is still bell-shaped, but it's a little wider. Basically, a lot of your data is spread out far from the mean. This would be indicative of high standard deviation. Doesn't matter which one you have, but you need to know which one you have, because if you're talking about finding the area to the right of some value, it could be wildly different depending on the shape of your curve. Okay, so it is very important that we know these numbers, right? If I want to be able to study the distribution of sample means and use calculate some probability here, I have to know the general shape of that bell-shaped curve. Mainly, I need to know where's the middle and how spread out is the data. Okay. Now, if we're talking about population proportions, same thing happens. Okay, so if we're trying to study, again, the population of registered voters in the country that are registered as Democrat, and if we were to look at a bunch of samples, like say, okay, we look at this group of 100 people and find the proportion that are Democrat, now another group of 100 and find the proportion that are Democrat, and now another 100. That end result, the distribution of sample proportions, would also be normal. And it would also show that the average of value of that proportion is the same as the true population proportion. And like we saw up here with means, okay, the standard deviations would not be the same. They would be off based on this formula right here. And on that applet that I used on StatCrunch, you could do the same thing. I selected mean. You could just select proportion, and it'll show you the same type of a graph. P is the proportion, all right, the population proportion. All right, again, it's the percentage, but it's just a percentage in fraction form. Q is its complement, so it's equal to 1 minus P. Right? So if Q is the proportion of Democrats, maybe, then Q would be the proportion of non-Democrats. Okay. All right. So the big one now. Let's talk about the big theorem, central limit theorem. Okay. It tells us about the shape of our sampling distributions. Again, which I could use those distributions because they're easy to analyze. I can analyze them to learn something about the population that may not be easy to analyze. In fact, it's not even necessary to know that the original population is right skewed. What we're going to see is that as long as I sample properly, it doesn't matter what this starts out as, whether it's skewed or any funky weird shape. If you sample sufficiently, the distribution of sample means or sample proportions or whatever is going to look normal. And so you will always be able to analyze this even if you have no idea what the population looked like. Okay, so it's a very powerful theorem because it's hard to know what the distribution of a population looks like, but it's easy, or it can be done, to take samples. Okay, so what this tells us is that the distribution of sample means will be approximately normal if, here's the two requirements, either the population was originally normally distributed or you take a sample size that is at least 30. Okay, so if your original population was normal, then your distribution of sample means is going to be normal. Okay, And again, by distribution of sample means, I mean when you do a lot of sampling and find a mean and a mean and another mean, you're going to get something that is bell-shaped. Now, we may not know the distribution of the original population, or we may know it, but it's not normal. So another tool or another way that we can use to determine if our sample means will be normally distributed is as long as we make sure that our sample size is at least 30. As long as we do that every time we take a sample, we're going to take a sample of at least 30, then again, I'm going to get my sample means to kind of fall down in a uniform normal distribution. So this is what we kind of refer to as the nearly large, or the large enough to be nearly normal condition. Okay, so it's not going to be exactly normal, but it's going to be close enough that we can use our methods for calculating probability of a normal distribution to talk about the distribution of these guys, the sample means. The same thing is true for proportions. Okay, so central limit theorem tells us that the same thing works on proportions, that your proportions, your sample proportions, all those p hats, they will be normal if the number of expected successes and fails is at least 10. Okay, each of those has to be 10. So this would be the expected number of successes. Okay, n times p, the sample size times the proportion that are considered a success, or Democrat, or whatever it is you're classifying as a success. Together those come out to 10. Same for the number of fails, right? The number of fails, all right, as long as that is greater than or equal to 10, then we would consider, or we would know that the sample proportion, the distribution of sample proportions would all be approximately normal. So, for example, again, if I'm talking about looking at Democrats versus non-Democrats, as long as I get enough people sampled that I'm going to have 10 people say, yes, I'm a Democrat, and then 10 people say, no, I'm not a Democrat, that's enough to ensure that all these p hats, again, just like with the sample means, they're going to fall down in a normal distribution pattern, some nice bell-shaped curve that's easy for us to study and analyze. Okay. So let's try some examples here. All right, let's see if we could make sense of some of these. It says that a population has a mean of 30, mu equals 30, and a standard deviation of 2.5, and it is slightly skewed to the right. A sample size of n equals 40 is randomly selected from this population. Describe the sampling distribution of x bar. Okay, so again, they're saying there's some population that is slightly skewed to the right. We know for this population there's a mean of 30 and a standard deviation of 2.5. Okay. Now, from this population, we're going to take samples of size 40. So I'm going to take 40 things, and I'm going to find the mean of those guys. So I'm going to take 40 things, find their mean. There it is. And I'm going to do it again. 40 different things. And find their mean and plot it down. And again, and again, and again. And I'm going to just take a bunch of sample means. It's a sampling distribution, so it's going to give every possible sample mean that could occur. They want me to describe the shape of the sampling distribution. This guy, what is this shape here going to look like if I were to continue doing this? Well, your gut may be saying it's going to be normal. Okay, that if you do it, we just kind of learned that if you do this, it's going to be normal. True, but under what conditions will it be normal? We have to make sure we match the conditions. So before I just go ahead and say, oh, it's normal and it's bell-shaped, why? If you look back, we had to say either one of two things had to happen. when we're talking about the distribution of sample means, either the original population was normal. If that's the case, then the distribution of your sample means is normal, but that's not the case here, right? Because for this guy, we know this wasn't normal. This was right skewed, okay? 2, the other way to claim that this stuff is going to be normal is as long as your sample size is at least 30. Well, here my sample size is 40. Okay, so what that means is that I'm sampling sufficiently large enough sets of data, okay, whatever it represents, so that's going to ensure that all of my sample means will indeed fall in a nice normal distribution. So let's describe socks. Okay, so let me just write a little note. Since n equals 40, which is greater than 30, central limit theorem tells us that the distribution of x bars is normal. Distribution of sample means is approximately normal. So if we're going to describe the shape, well, we know that a shape would be normal or bell-shaped. Symmetric, if you want to throw that in there, but normal gets the idea across. O for outliers. And there might be, but based on this information, we can't tell. I mean, we have no data, right? To determine if a data value is an outlier, you have to actually know a data value. Here they just gave me some parameters. Center. And so again, we're talking about the center of this guy. Where's the center of my sampling distribution? Well, if you recall, the mean of your sampling distribution, the mean of your x bars, is the same as the mean of your population, which they told us was 30. So we have a center of 30, and the spread we can talk about a couple different ways, but we've learned kind of the best is to talk about standard deviation, right? That tells us how spread out the data is. High standard deviation means it's really spread out. Low standard deviation means that it's not very spread out, that it's tightly compact around the mean. Well, the standard deviation for my sample means, if you look at the formulas on the previous page, it is equal to the population standard deviation over the square root of your sample size. So here we had a population standard deviation of 2.5 and a sample size of 40. So if we figure that out, that should be 0.395. That would be my spread, all right, the standard deviation of this sampling distribution. Okay, let's try this next one. I think the same idea. It says a population this time has a proportion of p equals 0.75. All right. A sample size of 115 is randomly selected from the proportion. Describe the sampling distribution of p hat. So again, here they don't tell us what the distribution of the population looks like at all, right? They didn't, up above they said it was right skewed. This we have no idea. It could be, who knows what it looks like, okay? But what they do tell me is that there's this population proportion of 0.75 or 75%. So maybe it's the proportion is I don't know, it's Californian. Maybe that's the, I just keep going back to political party affiliation. Maybe that's the percentage or the proportion registered as Democrat. The idea here is from this distribution, whatever it looks like, if I take a sample size of 115, so I'm going to take 115 data values, find the percentage or the proportion of those that are Democrat or whatever it is you're studying, and I'm going to record the sample proportion there, the proportion for that one particular sample. And then I'm going to do it again. grab 115 new data values at random, and they're going to give me another sample proportion. And again and again and again, and if we meet the requirements, we know that they're going to come out looking normal. Right? So again, what are those requirements? If you look back at the previous page, for a sample proportion, we needed the number of success and the number of fails to each be greater than 10. Now, success was found by taking the sample size times the proportion itself. If that's bigger than 10, that's the number of Democrats you can expect. If it's more than 10, you're good to go. Number of fails is NQ. All right. As long as that's bigger than 10, you're good to go. Well, here we know that P is 0.75, so Q, being the complement, would be 0.25. We know that N is 115, so let's see. The number of success, that's NP. That's 115 times 0.75. That is 86.25. That's greater than or equal to 10, so we're good there. The number of fails, that's N times Q, which is 115 times 0.25. That's 28.25. That's greater than 10. We're good there. So what that means is that, therefore, by the central limit theorem, the distribution of p hats is normal. Dist of p hats is approximately normal. And so if they want me to describe the sampling distribution, well, I'm going to go with socks again. The shape, that's normal. So I'm trying to write small here. Outliers, again, they gave me no data, so I can't tell. No data. Can't determine that yet. Shape, outliers, center. Remember, like in the previous example, if I want the population proportion, right? Or I'm sorry, I'm talking about the center. I'm talking about the average of these guys. So the average of these proportion values, these sample proportions, we learned that that's going to be the same as the population proportion, which was 0.75. That would be the middle here. And then spread. Again, if I want to talk about the standard deviation of all those sample proportions, which again, it's really important to know, because if you want to analyze this, knowing it's bell-shaped isn't enough. You have to know where's the middle and how spread out it is. So these are really important to know. But the formula on the previous page tells us to find this. We take the square root of P times Q over N. So this would be the square root of 0.75, 0.25 over N was 115. That's 0.040 if I typed it in my calculator correctly. So that's the spread of the thing. We are going to see where we really get to put this to a lot of use in the next coming chapters. I mentioned at the beginning of the video that this is the last major tool we need to get to hypothesis testing and confidence intervals, which is pretty much the whole reason to take this course, is to kind of get to those ideas. So the examples we're looking at now are really just helping us to find these. The mean of the sample means and the standard deviation of the sample means, the mean of the sample proportions and the standard deviation of the sample proportions. we have to be able to calculate those because we have to know what that distribution looks like in order to do advanced analysis on it, which is coming up. Okay, so we got a couple examples and then we're done. Let's take a look at example 3 here. So first of all, let's look at this table. What they've done is they've given me this table for males and females. They're using population notation, so this must be the population mean of all males, the population mean weight of all females, the population standard deviation for the weight of males, and the population standard deviation for the weight of females. And they tell us the distribution or the shape is both normal for males and females. Okay, so the data they're looking at are the weights of males and females. They're saying they're normally distributed with that mean and that standard deviation, center and spread. Okay. All right, so let's take a look. It says when designing life rafts, an obvious important consideration is the weight capacity. So Saks Shipping purchases life rafts that have a capacity of 16 passengers and a total weight of 2,400 pounds. Suppose the life raft is loaded to a capacity of 2,400 pounds with 16 males. Find the mean weight of the passengers. So they're talking about basically one sample. Okay, so again, first of all, let's kind of get our heads around the idea. We're talking about boats or life rafts that can hold 16 people and up to 2,400 pounds. And obviously we want to make sure that, we're not likely to exceed that. So they're just saying, suppose we take a sample, we've got a fully loaded boat, where what was the dead-on number? If we had exactly 16 males and they added up to exactly 2,400 pounds, what's the average weight per male there? So the mean of that sample would be 2,400 pounds divided by 16 people or 16 data values. That's 150 pounds on average. So each person in that boat weighs an average of 150 pounds. Okay, so here it says, well, find the probability that one randomly selected adult male has a weight greater than 150 pounds. Okay, because you might be thinking of some adult males that weigh more than 150 pounds. Some less, but some more. So what's the probability that if you pick an adult male at random, that they're going to exceed that? That's what this question is asking. Well, they tell us, so now I'm going to use this info up here. They tell me that for the weight of adult males, it's normally distributed with a mean of 182.3 and a standard deviation of 43.8. And they're saying, okay, 150, so if the mean is at 182, 150 is left of that, maybe there's 150. What's the probability of getting a male, so just one data value, one male, to be greater than 150? So that's this area we're looking for right here. Well, if you remember what we did in chapter 6.2, this last section, you've got two ways of calculating this. One is pull up StatCrunch and tell it this info, tell it the mean and standard deviation, and ask it that question. That's the fast way. The other way is you could find a z-score for 150 and do it with the z-table. So option 1 is StatCrunch. It's the fast one. Option 2 is a z-table. Let me just set that one up real quick. If you want to make a z-table, remember you first have to find the z-score. And so a z-score is, again, your data value minus the mean over the standard deviation. So in this case, let me see what that would be. I would get a z-score of negative 0.737. Okay, so what I could do is, once I find the z-score, now I'm talking about the standard normal curve, right? Remember, the standard normal curve has a mean of 0, standard deviation of 1, so that 150 converts into a z-score of negative 0.7 4, let's just say, and I want the probability of getting a z-score bigger than that number. Well, remember, your z-tables only tell you the left side of the area, so you'd have to find that area on your z-table and subtract it from 1 to get this answer. Okay. Let's just do it real quick on StatCrunch to make things faster. So let me go back to StatCrunch. Let's close this. See, remember I want to calculate on a normal distribution. My mean is going to be, for the males it was 182.3, the mean, and the standard deviation was, where did that go, 43.8. And I wanted to know the probability that we're greater than 150. All right, and so it tells me that the answer would be, I don't know why the screen is all up like that, but 0.2304. So let's just say 0.23 would be the probability there. Oh, whoa, look at this. I did left area. That's not what I want. I want right area. So I can do two things. I can either subtract this from 1, because that'll tell me all this area to the right, or I can just change this, and it converts it over there. So 0.769 or 0.77. So this is 0.769. Okay. Okay, so again, if I've got a fully loaded life raft that can hold, it's at weight capacity, 2,400 pounds. It's got 16 people in there. That means each person is averaging 150 pounds. Well, the probability of selecting a person that weighs more than 150 pounds is pretty good. It's almost a 77% chance you're going to do that. That doesn't sound good for our life raft. Okay. Well, this next question is slightly different. This says find the probability that a sample of 16 randomly selected adults has a mean weight greater than 150 pounds. Because what we just did is we talked about finding the average weight of a single person, okay, being greater than 150. That's not entirely what we're interested in. We're interested in, well, if I were to grab 16 people, what is the probability that together their collective average weight would be greater than 150? Meaning I know I can have some people that weigh 200 as long as I have some people that weigh 100. So if I grab 16 people at random, I want to know what's the likelihood that collectively they will have an average weight greater than 150. Okay. So what we're talking about now is we're talking about finding the probability of a sample, all right? A sample mean. Okay, so we are investigating sample means. So therefore we need to know, okay, I'm looking at sample means. If I want to know how to do probability, I have to know what type of a distribution we come from, right? We learned to calculate probability of these more advanced random variables. You got to know, are we dealing with something that's binomial or uniform or what? Well, we know that my sample means, right? Sample means are normally distributed if one of two things. The original population was normal, or 2, if your sample size is greater than or equal to 30. Well, here my sample size is 16, so option 2 is not good for me. But we do know, or we were told, that the original population was normal. Remember, the weights of adult males is normally distributed. It says on the table on the previous page. So what that means is that if I look at a bunch of samples of 16 people, I take 16 adults and I get their average weight. Take 16 adults and I get their average weight. Take another 16 and get their average weight. And I do this over and over and over and over and over and over. I'm going to get something that is normal. Well, and that's good, because what this question is saying is find the probability that my sample mean will be greater than 150. So here I don't want the probability that x is greater than 150. That's talking about a single person. I'm talking about the average of a group of 16 people. I want to know that the average weight among a group of 16 people, whether or not that exceeds 150. Okay. Well, again, to do probability, you got to know what the distribution looks like. I know this dude is normal, but I need to know a little more than that. Remember, I have to know what is the center and what is the spread, so that I know what I have to tell StatCrunch what these two things are, so it knows whether this is a skinny graph or a wide one. Right? Well, remember the sample mean, the mean of my sample means, I trip over those words, is the same as the population mean, which on the previous page it said the population mean for males was at 182.3. And the sample standard deviation is the population standard deviation over the square root of n. So it was 43.8 for the population over the square root of 16, my sample size. That's 10.95. I need to tell StatCrunch those two things in order to calculate this probability. So let's do it. On StatCrunch here, let me see if I can fix this. Come on, dude, work with me here. Try it this way. Okay, so let me go to Stat Calculator. Again, I want a normal one. Now here, the mean for my distribution of sample means, the mean is the same as the population mean, and the standard deviation is not the same as the population standard deviation. Remember, that was the population 1 over the square root of our sample size, so that came out to 10.95. And we're trying to find the probability that our sample mean, now they don't provide the x bar, but based on our numbers, we know that's what we're looking at, is greater than, 150, right? And that is a greater than, yeah, okay. That is a 99.8% chance that's going to happen. That's really not good for the life raft. Or I guess for the people on the life raft, rather. So this is a 0.998. 99.8% chance probability that if you get a group of 16 adult males together, that their average weight will exceed 150 pounds. That doesn't sound quite right, what I just said up there. Really, you got to think about it as out of those 16 people, if you were to find the average weight of an individual out of those 16 people, that would exceed 150 pounds. The probability of that happening is 99.8% chance. If you got 16 people together, you know they're going to exceed 150 pounds altogether. So that's not the question. It's just saying that out of a group of 16, the average weight of an individual in that group being greater than 150 pounds is pretty damn good. Okay. Let's take a look at this last example. A large university with over 25,000 students has 73% of the student population drive to school. So this is a proportion now, right? So this is a population proportion, 0.73, or 73 out of 100. So big university, 73% of the students drive to school. So suppose the parking and transportation department doesn't know this info, so they're trying to figure it out. They conduct a survey of 1,000 randomly selected students and ask them whether or not they drive to school. Okay, so what they're doing is, again, for this original population, we have no idea what it looks like, all right? But what we're saying is that they ask 1,000 people, and they find the percentage of those 1,000 people that drive to school. Maybe it's 70%. So they get a sample proportion, and then they go ask another 1,000 folks whether or not they drive to school, and they get a new sample proportion out of that batch, and so on and so forth. And they repeat and they repeat and they repeat, and they're probably going to ask us some probability about these sample proportions, like saying if you were to grab a group of this many people, what's the likelihood that we would expect this percentage to drive to school? Well, You want to do probability, you got to know the shape of the distribution. And under the right conditions, we know this will be normal. Okay, so let's see if we've met those conditions. Verify that the distribution of p hats, these guys, is approximately normal. Remember, for proportions, what we have to do is we need the number of successes, which is equal to n times p. That has to be greater than or equal to 10. Well, n is 1,000 in this case, right? That's my sample size is 1,000. P is the proportion of people that drive to school. That's 730. It's well above 10. And same, we need the number of fails, which is n times q. If 73% of students drive to school, then q would be the 27% of students that do not drive to school. That's 270. Again, well above 10. So, therefore, the distribution of p hats are approximately normal by the central limit theorem. The distribution of p hats is normal, or approximately normal. Okay, so here they're saying, well, what is the probability that p hat will be more than 3% away from the true proportion? Because remember, there is some true proportion of people that drive, and it's the same that we would see here. It's the same as the mean of all those sample proportions. It's the same as the population proportion. So they're saying, what's the probability that you're going to get a p hat, like that this guy is going to be more than 3% away from the true proportion? Okay, well, let's think about that. These p hats are normally distributed. The true proportion is right here. Right? It's the average of your sample proportions, which is the same as the population proportion, like I just said. And I want to know what's the chance that it is more than 3% away. Well, 3% beyond that, if I add 3% to this, I'm at 0.76. And if I go 3% the other way, so this is going plus 3%, if I subtract 3%, I'm at 0.70 or 70%. And they want to know what's the probability of being beyond that. So what's the probability of landing here or here? Okay. So again, they're saying if you were to grab a p hat at random, what's the probability that it's there or that it's in this tail, that it's more than 3% from the middle, okay, the true proportion? Well, I can do this easy enough in StatCrunch. All I need to do is tell StatCrunch a little bit about this normal distribution. Remember, I'm going to go to Stat and Calculators, and then it's going to say, okay, well, what's the average you're using? Okay, well, we just said that's this guy. And then it's going to say, well, what's the standard deviation of that distribution? Well, if you remember, there's a formula for this. It's NP, nope, how about it's P times Q over N. So if I plug in these values, I get P is 0.73, Q is 0.27, and N is 1,000. That is 0.014 if I calculated it right. So StatCrunch is going to need those two numbers from me so it knows exactly what the shape of this distribution looks like, and I can then therefore calculate probability. Okay, so what I'm looking for is the probability that I'll get a p hat, well, that lives in either of these arms. So remember, by symmetry, can't I just maybe find one of these and double it up? So maybe I'm going to say it's the probability that p hat is less than 0.7, and I'm going to double that up. I'm going to take 2 times that amount. Okay. So let me go back to StatCrunch. I got the normal calculator up, but again, my mean is now 0.73, and my standard deviation is 0.014. 0.1014. And I'm looking for the probability of being less than 0.7. That is 0.16. Oh, sorry, 0.016. Okay, so let's go back to the notes. This is 2 times 0.016, so that would be 0.032. Okay, this is the probability that p hat will be more than 3% away from the true proportion. Okay, I hope these problems make sense. I promise you, once you kind of get the hang of them, they really aren't bad. And really, the problems you encounter in this section is not really typical of the way we want to use this theorem. I mean, it's definitely an application of this theorem, but it's not the type of questions we're really interested in answering. Again, they're just really getting you to practice this idea that given some scenario, can you recognize that your sample means or sample proportions are normal by verifying the correct, requirements, whether it's a proportion or a mean, and then making sure you can figure out these two numbers so you can either find the z-score to calculate probability or tell StatCrunch what it needs to know to calculate probability. That is what all of these homework questions are doing in some way or another. They're giving you a scenario and having you investigate the distribution of sample proportions or sample means. And again, the two things are make sure you can verify that it's normal. Does it meet the requirements to be normal? And can you find those two things? Because you'll need that to calculate the probability. So that's what 7.1 is all about. It's about learning that these things are normal, and the homework is about practicing those two skills. And I'm real excited for us to get into Chapter 8 and onward because, again, you've now finished up the last tool you need to get into what statistics is really kind of about, which is running some tests, hypothesis tests and things like that, and building confidence intervals. So we are right there. Okay. In class, when we do the practice problems, I'm going to make some up, and I think I've got a few homework problems in mind that I would like to do as well. Also, you'll notice that there's 2 homework assignments for this, for 7.1. There's one called 7.1 Sample Means, and then the other one should say 7.1 Sample Proportions. It doesn't quite say that. It does mention sample proportions. So the homework is split up into 2 parts. The first part is all about means, and the second part is all about proportions. Okay, so there are 2 homework assignments for this, all right? All right, thanks for sticking through it. I'll see you in the next one.